Imagine trying to measure the exact moment a car reaches its top speed. Or perhaps you need to determine the precise area of a curved surface. These tasks seem impossible at first glance because they involve infinitely small changes over infinitely small periods. This is where the beauty of calculus and its fundamental concept, limits, come in. Calculus deals with change, and often that change is continuous and instantaneous. To understand these changes, we need a tool to dissect them without getting lost in the infinitely small. That's where the concept of a limit comes into play. In essence, a limit is a way to sneak up on a value without actually reaching it directly. It's like whispering a secret as closely as possible without ever uttering the words aloud. Limits allow us to study the behavior of functions and equations as they approach specific points, revealing hidden patterns and truths. Imagine watching a video of a bouncing ball, but a few frames are missing. You see the ball in one position, then it disappears for a moment and reappears in another position. Even though you can't see the ball at those exact moments, you can make a good guess about where it was by observing its position in the frames just before and after the gap. Your mind fills in the missing information. This is a simple analogy for a limit. In mathematics, limits help us understand the behavior of functions as they approach a certain point. In mathematics, a limit is our best prediction of a function's output, the y value, as its input, the x value, gets infinitely close to a certain point, even if we can't reach that point directly. It's like predicting the ball's position, even when we can't see it. Think of it as a game of getting closer. As the input gets closer and closer to the target value, the output gets closer and closer to the limit. This concept is fundamental in calculus and helps us solve complex problems. The power of limits lies in their ability to give us meaningful information, even when traditional methods fail. They allow us to make sense of situations that seem impossible to analyze. This is especially useful when dealing with situations involving infinity, division by zero, or instantaneous rates of change. Limits provide a way to navigate these challenging scenarios and find solutions. Limits are not just abstract mathematical concepts. They have real-world applications that are all around us. They help us understand and navigate the complexities of our daily lives. Think about digital images. Every picture on your phone or computer is made up of tiny squares called pixels. These pixels are the building blocks of digital imagery. Each pixel has a specific color, and when you zoom in close enough, you can see these individual pixels. They appear as distinct, separate entities. However, from a distance, these individual pixels blend together, and we perceive a continuous image. The individual squares disappear, and a cohesive picture emerges. This is a visual representation of a limit. It shows how discrete elements can come together to form a continuous whole. Another example is the speed of a marathon runner. When we observe them, we often think about their overall performance. We can talk about their average speed over the entire race, but what about their speed at a particular moment? This is where things get interesting. It would be impossible to measure their speed at a single instant, because that would require dividing the distance traveled, 0, by the time elapsed, also 0. This paradox highlights the challenge of pinpointing an exact moment. However, we can use limits to approximate their instantaneous speed by calculating their average speed over progressively shorter and shorter time intervals. This method allows us to get closer to the true value. These examples show how limits help us bridge the gap between the discrete and the continuous, allowing us to make sense of the world around us in a more nuanced way. They provide a powerful tool for understanding complex phenomena. One of the most powerful aspects of limits is their ability to provide answers in situations where traditional mathematical operations break down. For example, what happens when you try to divide by 0? Your calculator will probably give you an error message, but limits offer a way to explore this seemingly impossible scenario. Consider the function f(x) equals sine 1x. As x gets closer and closer to 0, the value of f(x) gets larger and larger, approaching infinity. While we can't actually divide by 0, the limit allows us to describe the behavior of the function as it gets infinitely close to that forbidden value. Similarly, Limits help us grapple with the concept of infinity. While infinity is not a number we can plug into an equation, we can use limits to describe what happens as a function's input or output grows infinitely large. Section 5. The importance of limits, building blocks of calculus. Limits are not merely a tool for solving specific problems. They are the very foundation upon which calculus is built. They help us understand the behavior of functions as they approach specific points, or even infinity. The two main branches of calculus, differential calculus and integral calculus, rely heavily on the concept of limits. Without limits, these branches would not have the rigorous mathematical framework they need to solve complex problems. Differential calculus, which deals with rates of change, uses limits to define the derivative of a function. The derivative is a fundamental concept that describes how a function changes as its input changes. The derivative tells us how much a function's output changes in response to an infinitesimally small change in its input. This is essential for understanding dynamic systems and processes. This concept is crucial for understanding everything from the speed of a rocket to the growth of a population. It allows scientists and engineers to model and predict real-world phenomena accurately. Integral calculus, on the other hand, uses limits to define the definite integral, which allows us to calculate the area under a curve. This is vital for determining quantities like total distance traveled or the accumulated growth over time. This has applications in a wide range of fields, including physics, engineering, and economics. Professionals in these areas rely on integral calculus to solve practical problems and innovate new solutions. Without a solid understanding of limits, it would be impossible to grasp the powerful tools and concepts of calculus fully. Mastery of limits is essential for anyone looking to excel in mathematics and its numerous applications. Section 6. Zooming in. Understanding the formal definition of a limit. While the intuitive understanding of limits is crucial, mathematicians require a more rigorous definition. This is where the epsilon-delta definition comes in, providing a precise way to prove the existence of a limit. Imagine using a powerful microscope to zoom in on a point on a graph. As you zoom in closer and closer, the behavior of the function around that point becomes clearer. The epsilon-delta definition formalizes this idea of zooming in to prove that a limit exists. This definition, while initially daunting, is essential for establishing a solid mathematical foundation for limits and ensuring their reliability in complex calculations. Section 7. A dance of precision. The epsilon-delta definition. The epsilon-delta definition involves two key players, epsilon and delta, both representing incredibly small positive numbers. Epsilon represents the desired level of accuracy or closeness to the limit, while delta defines the corresponding window of input values around the point we're approaching. In essence, the definition states that for any desired level of accuracy, we can always find a small enough window around the input value, such that all the function's outputs within that window lie within the desired accuracy range of the limit. This dance between epsilon and delta, where epsilon sets the challenge and delta rises to meet it, ensures that our prediction of the limit holds true no matter how stringent our accuracy requirements are. Section 8. Limits at infinity. Approaching the unreachable. Limits are also instrumental in understanding the behavior of functions as their input values grow infinitely large or infinitely small, approaching positive or negative infinity. While we can't plug in infinity directly into an equation, limits allow us to analyze the function's tendencies as it heads towards these boundless realms. For instance, consider the function f of x equals 1 over x. As x approaches positive infinity, the value of f of x gets closer and closer to 0. This doesn't mean that f of x ever actually reaches 0. Rather, it indicates that the function gets arbitrarily close to 0 as x grows infinitely large. Limits at infinity are crucial for understanding asymptotic behavior, where a function gets infinitely close to a line or another curve without ever actually touching it. Section 9. Conclusion. Limits, a gateway to understanding our world. Limits, while a fundamental concept in calculus, extend far beyond the realm of abstract mathematics. They provide a framework for understanding change, continuity, and the behavior of systems in a wide range of disciplines from physics and engineering to economics and biology. Whether it's analyzing the speed of light, modeling population growth, or understanding the behavior of financial markets, limits provide the essential tools for grappling with the complexities of our world. By embracing the concept of limits, we gain a deeper appreciation for the nuanced and ever-changing nature of the universe around us.